Hello everyone. In this video we are going to see about the noise models. I am Dr. Inbamalar, working as professor in the Department of Electronics and Communication Engineering, RMK College of Engineering and Technology. So before going to the noise models, let us see about image enhancement and image restoration. So all of us know basically an image will be captured, pre-processed, then undergoes image enhancement or image restoration. So the fundamental objective of both the techniques are same, but image enhancement is a subjective process, image restoration is a objective process. Objective process means here we will be having mathematical fundamentals to decide on the restoration technique. And when you have the image, when it is captured, there will be a distortion introduced which degrades the image. So fundamentally the captured image will be analog in nature and it will be converted to digital image. So there will be sensors and allied analog to digital circuitry involved in the capturing and further processing of the image. So we can understand some distortion happens during capturing. And the principal sources of this distortion arise due to image acquisition and or image transmission. So if you see, the performance of imaging sensors is affected by a variety of environmental factors during image acquisition and by the quality of the sensing elements themselves. So if you are using a CCD camera for acquiring images, light levels and sensor temperature are major factors affecting the image quality. When you transmit the images are corrupted by interference in the transmission channel. Images when transmitted using a wireless network, that can be corrupted by lightning or other atmospheric disturbance. So these are the some of the examples for the distortion. So like this, there are varieties of distortions while capturing and transmitting the image. So since we are studying image restoration process, all this disturbances to be modeled mathematically. So that is what the noise models refers to. And when we come to mathematics, we know noise is an unpredictable, instantaneous, random variation. So the mathematical discipline which deals with this uncertainties is probability. So we are going to model this noise using probability density functions. Here also the image is f of x comma y and the noise is represented as n of x comma y. So now depending on the type of disturbance, this noise can be classified under various standard probability density functions. Accordingly, I am going to tell you about Gaussian noise, Rayleigh noise, Erlang noise, otherwise called as gamma noise, exponential noise, uniform noise, salt and pepper noise. Let us see one by one. First, let us start with the Gaussian noise. So because of its mathematical tractability in both the spatial and frequency domains, Gaussian noise models are used frequently in practice. The probability density function of a Gaussian random variable z is defined by P of z is equal to 1 by root of 2 pi sigma into e power minus z bar the whole square by 2 sigma square. Here z represents the intensity, z bar is the mean value or average value of intensity, and sigma is its standard deviation. So now the probability density function of this Gaussian distribution can be considered as equivalent to the Gaussian noise. This tells you the noise is symmetrically distributed above the mean. So you see it is a bell curve. The maximum noise appears at the mean Z bar and it decays symmetrically on both the sides. Now let us move to Rayleigh noise. The probability density function of a Rayleigh noise is given by P of Z is equal to 2 by B Z minus A e power minus Z minus A the whole square by B for Z greater than or equal to A and 0 if Z is less than A. Mean of this PDF is given by A plus root of pi B by 4 and variance sigma square is equal to B into 4 minus pi by 4. So this is actually not a symmetrical distribution. This is a skewed distribution. Here the probability density function is skewed to the right. This is useful for modeling the shape of skewed histograms. Next, Erlang noise, otherwise called as gamma noise. The probability distribution function is given by P of Z is equal to A power B Z power B minus 1 divided by B minus 1 factorial into E power minus A Z for Z greater than or equal to A, 0 if Z is less than A. A greater than 0 and B is a positive integer here. The mean of this PDF is given by Z bar is equal to B by A, variance is equal to B by A square. This is also a skewed curve. Here the distribution is skewed towards the left. Next, exponential noise. PDF of the exponential noise is given by P of Z is equal to A into e power minus Z if Z is greater than or equal to A and 0 if Z less than A. A should be greater than 0. The mean and variance are 1 by A and 1 by A square respectively. Exponential noise, maximum at the origin and decays exponentially. Next, let us come to the uniform noise. Uniform noise, probability density function will be uniform. So, P of Z is equal to 1 by B minus A for A less than or equal to Z less than or equal to B, 0 otherwise. Mean is A plus B by 2, variance is B minus A the whole square by 12. Uniform noise, you can visualize here from A to B. The probability is 1 by B minus A which is constant and 0 to A and B to infinity it is equal to 0. Now let us come to salt and pepper noise. This is otherwise called impulse noise. Here when Z is equal to A, P of Z is equal to PA. When Z is equal to B, P of Z is equal to PB, 0 otherwise. So now if B greater than A, the intensity appears as a light dot, that is bright. If intensity A is greater, it will appear like a dark dot. Neither PA nor PB is 0, and especially if they are approximately equal, the impulse noise values will resemble salt and pepper granules randomly distributed over the image. So here we can say three types of noise. One salt noise, other one pepper noise, other one salt and pepper noise. If there are only bright spots, it is called salt noise. If there are only dark spots, it is called pepper noise. If both bright and dark spots appear, it is called salt and pepper noise. So here we can visualize the probability density function. You have an impulse signal with the probability PA, PP. So let us summarize. This noise models will be helping us to select the appropriate restoration techniques. So when you are given an image, you have to take the histogram of the image, compare with the probability density function. The histogram matches with the particular probability density function means we can assume that type of noise is present in that image, and accordingly we can go for the corresponding filtering techniques. Thank you.